What are weights and biases in neural networks? Imagine teaching a robot to recognize your favorite fruit. You show it many apples and bananas. Over time, it learns which features matter most. That's where weights and biases come into play. They are the core parts that help neural networks learn from data. Weights are like volume knobs for each piece of information. When data flows through the network, each input is multiplied by a weight. If the weight is high, that input has a bigger say in the final decision. If it's low, it's less influential. During training, the network adjusts these weights to get better at recognizing patterns. Think of it as tuning a guitar until the sound is just right. Biases are a little different. They are added to the total of weighted inputs before passing through an activation function. They act like a starting point or a baseline. If all inputs are 0, biases can still push the output in a certain direction. This helps the network make accurate predictions even when the data is simple or minimal. Together, weights and biases shape how the neural network processes information. They allow the model to fit complex data patterns, like recognizing faces or understanding language. When training a neural network, the system compares its predictions to actual answers. It then tweaks the weights and biases to reduce errors. This process is called optimization. Properly adjusted weights and biases help the neural network perform well on new data it has never seen before. This ability to generalize is key for real-world AI applications. For example, in image recognition, the network learns which features are important, like edges or shapes, by changing weights. Biases help the model shift its focus when needed. Understanding these parameters also raises awareness about fairness in AI. If the training data is biased, the weights can reflect that bias, leading to unfair results. That's why careful training and monitoring are essential. In short, weights control how much influence each input has, and biases give the model flexibility to shift its responses. Both are vital for neural networks to learn, adapt, and perform tasks like generating text or creating images. Without them, deep learning models wouldn't be able to recognize patterns or make accurate predictions.